size of a shirt.
Yep. The colors,
Yeah.
the fabric,
Mm-hmm.
I don't know, maybe the texture, like the material used.
Yeah. Yeah. So all these make sense, right? Um, so all these like hidden variables, you can imagine uh, come together to produce like the concept of a shirt, or like to produce your shirt object, which you were holding in your, which you saw in the store, and then you took a photo of that, which produced the data set, produced the data.
Okay.
So that's a latent variable model you've just told me, because they're hidden variables generating our data, pixels, in this case, but could be anything, could be text as well. Oh yeah, any modality.
Okay. Yeah.
Right. So the concept of latent variable models kind of clearer now.
Uh, yeah. It. So. Okay. Yeah. Yeah. I think yes.
Cool. Um, yeah, I mean these are like examples of latent of things that are hidden from us, but I think we drove that point home. Right. So let's formalize it a bit. So our distribution is really x, which is our observed variables, and z, which is our unobserved variables. And this is the joint distribution between them. And we're going to make the assumption that it factorizes as such. That yeah, p of z, like we said, our generative story is like we if we were actually generating the data, we would get our hidden variables, like give assignments to them. So like pick a color of my shirt, red, pick a size of my shirt, some size, pick a clothing material, silk, whatever. And then given all our hidden variables, we produce our data, like an image of a shirt. Obviously, like we could design a seriously complex model of this, like maybe it's not just it might not just be like it's not this like p of x given z can be like arbitrarily complex, essentially, because you can imagine the real world is complex, so obviously this distribution might be complex.
You said that you assume that it factorizes like this, but it's an axiom of probability.
Oh yeah, that's true. The other
It's the product rule.
yeah. Um, so and this is like another, I guess another fact. The p of x, which is our generative model, essentially, the probability of our observed data, is essentially sort of the marginalization of our factorization up here. We're marginalizing out z. So this is the sum rule of probability. So yeah, as Noki mentioned, top rule, product rule. This marginal is the sum rule. Those are the only real two rules you need to know to follow this. Yeah, does that make sense?
Yep. I think so.
Okay, so given, I think I asked you this last time I was giving this presentation, but can you derive p of z given x given the two set of things up here? The product rule and the sum rule.
Yeah. I think at one point I did.
Okay, talk me through it.
Yeah, give me a second. Different rules.
And this is Bayes' theorem, right? Just
Yeah.
we're very clear on it.
Yeah, and this is actually what I was looking for when Googling. But yeah, now we see it in flesh.
I think it's more informative to write like, oh no, that's what BS is supposed to do. Never mind.
Yeah. Exercise for the viewer.
And I'm deriving it from the joint distribution.
I mean, you will need both of them. I mean, just show me the left-hand side is equal to the right-hand side is essentially what I'm asking you. You can do that however you'd like.
Oh, I see. Okay. Okay.
We should get like a notepad, a shared notepad.
Yeah. Okay. I can do that. Sorry, I'm just looking at the different the probability rules and trying to like find something.
Yeah, I'm just reading the comments now in Whiteboard. So wombat and combat. So in order to generate a data set, you would imagine the class you're going to generate in and then corresponding pixels. So yeah, that's a very simple latent variable model, but it is a latent variable model. You can imagine like a bunch of other factors rather instead of besides class, like brightness or kind of whatever, anything you just don't observe directly in pixels.
Like somehow doing this is actually how the data was made. Like these clothes were designed by people who were like, okay, I'm gonna make a shirt, and I need to make it of a certain size, and I want to have it with this style and this color, and then they like. So it actually was generated by them according to some process from these factors. So we're just like modeling that.
Yeah. Can I get the link of the presentation? I'll think about it. I'm not sure I want to share it.
Why?
I think it could be used to identify me, given I've presented this at multiple places.
When have you presented this?
I've done like a bunch of reading groups for this.
Is there another way to write P of something and something?
What? You gotta be more specific than that.
Just the and symbol, like
In like Boolean logic, it would be like pxz, right?
PXZ. What do you mean?
Like and instead of x comma z.
Oh, it's equivalent to the comma.
Yeah, is that what you're asking? X comma z is p of x and z.
Okay, I didn't.
It's the joint distribution of x and z.
Okay.
Do you want to talk out loud? Where are you starting from?
With the numerator, so
Okay.
the numerator is equivalent to our joint distribution. Define the slide, the p, x, and z.
Yeah.
Um, but
That's right. So you can do that substitution twice, actually.
yeah. But as far as like getting to the actually, yeah. So then p of x is equal to the integral of p of x given z times p of z. Um, but
Okay.
second. Yeah, and then once we have p of x and z in the numerator and p of x in the denominator, this is equivalent to p of z given x. Yeah, so that's the derivation.
Yeah. By what theorem?
I don't know what theorem. I'm just using the different rules. I don't know if
Yeah.
the theorems are equivalent to the rules, but
Conditional probability.
okay. Yeah. Yeah, I guess that works because it's also called the conditional rule.
Wait, say that again? Like, say the derivation again? Just so I...
Yeah, so the numerator is p of x and z equals
Mhm.
to p of z times p of x given z. So you just replace what the numerator currently is with p of x and z, and then you replace the denominator with its equivalent thing, which is p of x.
Mhm.
And you do this because we know that because of the conditional rule that p of z given x would be equal to what I just described.
I mean, it's not a rule. It's just the product rule. It's just the same as that joint distribution.
Sure. Yeah. I mean, the webpage that I'm looking at calls it the multiplication rule, but yeah.
Sure. So, yeah, just to like really make sure you understand it. So this is one way to write the joint distribution. What is the other way?
This is a question of like notation. Like, what do you mean?
No, I mean, like I can write this. I mean, okay, let me like.
When he applied the product rule, he could have applied it two different ways. What's the other way?
I mean, yes, right. Can you write what you've got in whiteboard?
Right.
Like you just told me like p. Oh, you just told me p of z given x is joint over p of x. Can you just write that down?
Yeah. One second.
Doesn't have to be later. We might be here for a while otherwise.
make more sense?
Okay. I mean, yeah, does. Cool. Let's proceed. So, looking at this formula, we're interested in like the inference problem. Well, we're interested in. I'm gonna say we're interested in the inference problem. You might be interested in learning there are basically multiple ways to derive the elbow, and you can either go with it from the inference perspective or from the modeling the actual observed variables, like generative perspective. But let's go with the inference method for now. So the challenge with this formula is like that like denominator, right? Like whenever you see an integral in ML, you should just feel scared unless very special conditions apply. So because what comes out of that might not be like might not have a closed form solution. So given that that's challenging, like how do we actually learn these? So maximum likelihood, as we've seen, not tractable. So I'm not going to present. I'm gonna take it like a tangent and go into. I mean, not really a tangent. It's more like an example of a latent variable model, a Gaussian mixture model, and show that an approach for solving this. So, what is a Gaussian mixture model? I kind of should have mentioned it like at the start, but let's go back to this. Actually, BS, you've been reading up on Gaussian mixture models. Try to explain Gaussian mixture models.
So it is a distribution defined by a combination of many different Gaussians scaled by some value to make sure that the total value of their what are they called? The total value of the I should say the cumulative probability is equal to 1.
Yeah, so the area under you take an integral of them from negative infinity. It's a probability distribution essentially. But okay, so yeah, that's one interpretation, or one way of like describing them. But you can actually.
I think maybe it's worth asking what does combination mean?
Yes.
Because a naive combination of Gaussians is just a Gaussian, right?
Yes.
A naive combination of Gaussians.
Like a sum of two Gaussians is a Gaussian. Do you agree? Like a sum of two independent Gaussians is a Gaussian.
No, I do not agree.
You do not agree that a sum of independent Gaussians is a Gaussian?
No, because when the cumulative probability wouldn't equal 1.
So you think the sum of two random variables is not a random variable?
I don't know.
I mean, what do you think? Like, I mean, you can reason through things, right?
One second. Yeah, I don't know.
I see. Well, you should check on your own that the sum of two Gaussians is in fact a Gaussian, or maybe more precise, the sum of two independent normal distributions is in fact a normal distribution.
Okay.
There's nothing else to say about that. But I think the key thing is that a mixture Gaussian is not just a sum of Gaussians, which is the point that I wanted to highlight.
Okay. So where were we? So yeah, like I wanted to give like the latent variable like interpretation. Um, of mixture models, right? So yes, imagine you have to generate the data here on the right. As you, I give you access to a function that can like take a mean, and variance and covariance, and produce samples from it. This just assume this function exists. How would you generate like the data on the right here?
From the data on the left.
So yeah, I give you to a function that can produce the data on the left. I mean, that can sample from. Yeah, I give you a function that can essentially generate a sample from a random Gaussian, 2D Gaussian. Now I ask you to produce, and you can plot these samples, obviously. Now, can you produce a distribution that looks like one on the right?
Yes. I mean,
Yes. How?
I mean, I don't know.
I mean, these are not like these questions like don't require like any prerequisite knowledge. It just requires you to be like creative. Like, give me your best attempt at it.
So it just given the data on the right, I'm supposed to like I should or rather I'm supposed to generate data that's like on the right. Like I don't even know. Like I don't know what like how to even do that.
But I said I gave you a function that can generate samples from a Gaussian, right?
Yeah.
So that is a distribution. Can you produce, given that, and you try, like, given that sampling function, like, give me, like, can you think of a way to generate the data on the right? By the way, this is like an unfair question, like, do point it out. If it like requires a bit of a leap, but I think it's reasonable.
Make copies of the Gaussian, and I don't know.
Sorry to interrupt. Where's the new whiteboard?
The new whiteboard?
Are you guys seeing something? Do you have a visual? Because I'm currently not seeing it.
Visual?
Yeah, you're still on the slides. Yeah.
I'm streaming, right?
Yeah, but it's just streaming the slides that you had open.
Yeah, we're talking about this one.
Yeah.
Oh, okay. Well, I thought that.
I think the question is
fair,
fair, but I don't think we should belabor it too much longer.
Okay, fine. Okay, fine. So it's these three, like, they're obviously like three. This is obviously it's like these obviously look like three different Gaussians, right? Because
Yeah.
so if we're thinking like in terms of like latent variable models, I might say I'm going to generate data from the first Gaussian. So that has a certain mean and variance associated with it, and I could roughly estimate it. Just like guesstimate the mean, guesstimate the covariance, and essentially get means and variances for each of these three Gaussians very easily. I mean, relatively easily. Yeah.
Yeah.
So now I actually want to generate the data. I have the means and variances, covariances. Now I want to generate the data. So I would just pick. So one thing we can see is like they roughly look of equal density. Like no one Gaussian is more dense than the others. So maybe we could think they're roughly evenly distributed amongst all three Gaussians, the number of data points. Is that right? Yeah. So we could think of a latent variable model that looks something like this. I define a uniform distribution over three I define a latent variable that is a categorical distribution of with three classes in it. Essentially, like imagine three classes: Gaussian 1, Gaussian 2, Gaussian 3. Ignore categorical if that doesn't make sense to you. I pick one of the three classes uniformly, so I'm not favoring any class over the other, and then I sample from that Gaussian. Now, if I repeat this process, I'll eventually get data that looks like this, right? Because I'm sampling evenly from all three Gaussians, and the data is eventually going to look something like this. Does that make sense? So what was my latent variable in this case?
The scaling factor.
Scaling factor?
Yeah, like the amount that like you're trying to best represent these different Gaussians with some kind of like scaling factor. Like obviously it's gonna be like mean or variance, but
Okay, parameters are not latent variables. Like, just because I don't know my parameters, I mean, you could treat them as latent variables, but I think in this case, I estimated them and I fixed them, right? So I estimated them like by just looking at it and trying to measure the means and trying to measure the variance. So in this case, the latent variable was the classes, right? I obviously don't know the classes from the get-go. Like given a data point, you give me a data point, I don't know which of the 3 Gaussians it came from. It's hidden to me. So
Why?
I mean, if I give you point 0, 0 on this plot, which Gaussian did it come from? Does the point 0, 0 alone tell you which Gaussian it came from?
I mean, assuming is it that each cluster, like, is each Gaussian a different class?
Yeah.
Yeah, so why can't I just look at, like, I can, like, tell, maybe, like, some of the outliers I can't, but, like, for the most part, I can tell which class each data point came from.
But the data points in isolation doesn't tell me which class it came from, right? It's a hidden variable. I give you just 0, 0, you're not allowed even to look at this picture. It's
okay,
hidden,
sure.
right? The class is hidden. Similar to the other latent variable examples I mentioned earlier.
Okay.
Like the class is hidden. So in this case, the classes there are 3 classes and they're roughly uniformly distributed. And we call, like, if it's a discrete, like one, this discrete variable is called like categorical distribution method. Because it, I guess, has categories, different categories. I don't know where the word name comes from. I'm assuming that. But this is essentially what a mixture of Gaussians is. It's like sampling, sample a category, pick the Gaussian associated with that category, and generate it. Make sense?
Yes.
Okay. Now, let's try linking back to this like formula we had down here. So I'm defining x as our observed variables and z as our latent variables. So in this case, we're going to be using, since z is discrete, it's a categorical distribution, 3 classes, or however many, an example above 3. So we're going to be, instead of the integral down here, we're going to use the sum, right? It's discrete set. And as you correctly identified, just given the data, I also need to estimate the parameters of my Gaussians. They are obviously not available to me, and estimating them by hand is non-scalable and impossible. So can you see how should I put, like, I wish I could put these like side by side, but you can see, can you see how like this is very similar to what you wrote down in whiteboard?
Yeah, I can.
Cool. So the EM algorithm is essentially an iterative approach to estimating both the parameters, well, the parameters of my Gaussians as well as the parameters of my categorical distribution, because it's not necessarily uniform. I said it was uniform, which means like a third in the three categories. But it's not necessarily uniform. It could be we could be weighing. We might want to sample. The data might come from a distribution which samples from one class more heavily than the other.
Oh, is this where this idea of the, well, I guess you told me not to do this, but is this where the idea of the unit Gaussian comes from? That like best.
I told you not to do this.
Okay.
Yeah. But in this case, actually, going back to this, let's give like things some names. So we don't actually have, instead of calling it P of Z and X given Z, let's give them like names. So P of Z, what does that mean?
The probability of Z.
Yeah, the probability of our latent variables. And generally, like, we call this like the prior, just because we are setting it as what we initially believe our initial instantiation, our instantiations of Z are. Make sense?
Yeah, I think so.
And what we have on the left-hand side is like the posterior. I'm just telling you that. It's like, this is just generally how people refer to things in the base rule, because this is base rule. Like if you go look up what base rule is, you'll see this. Like it's just you might see different variable names.
I understand the like where it's coming from. What I don't understand is like how do you even have the probability of a lane variable that you don't have access to?
Yeah, exactly. So you guess.
Yeah.
That's why we call it a prior, because
it's what we believe it to be.
If we want to calculate this P of Z given X, in the first place, when we don't know what P of Z is, we have to guess. Or if you want to say that more generously, it's we want to incorporate our prior knowledge of what.
I think that like this may be more like philosophical or epistemological. I mean, in some sense, like there may not even be a Z, like a real Z. We hope there is. We hope it captures something like real about distribution, but it doesn't really have to be some sort of Z with like meaningful interpretation. And once you abandon that, then you can really make Z whatever you want, right? Like mathematically, as long as Z has some nice properties, like, as long as the distribution Z has some nice properties, we can get any other distribution. So once you kind of like forsake interpretability, you might as well just choose convenient informations. Like you can say, okay, suppose that we have, suppose that we want our data to be modeled by a function of the Gaussian. How far can we go, and how would we do it? Then you would end up with something like this.
So how do you determine like what the best distribution to use for it? So because like what if like by the act of modeling something using like some assumed distribution it becomes so?
Yeah, I mean that's the whole point, right? You train a model so that you can get the best you can get with it.
The data is not affected by your modeling choices, right? The data is not independent of that. It's how you choose to model the data.
In fact, you don't need to like appeal to the existence of some like probability Z at all. This all works in terms of decision theory, so you can just say that P of Z is just your belief in Z, and everything works in.
Maybe more pragmatically, you should think of the prior as another modeling choice, right? Like, why do we use default layers or comments or whatever, right? Those are just modeling choices. So you can think of the prior as also being just modeling choice.
essentially, I'm not gonna give like an explanation as to like why the EM algorithm works. I'm just gonna tell you what it is. Just know that like whenever we do this, whenever we do like E and M, we're always like increasing the likelihood. So
Yeah,
that's
I
like a
think
nice guarantee.
Can I try and give at least the beginnings of like why I think the algorithm works?
Sure, go ahead.
At least from the derivation that I saw, I'm pretty sure you can derive. I know that you can derive the log likelihood and the KL divergence, and there's one other like third extra term that comes out of EM, but it basically gives you these three terms that like allows you to like determine not only like the I guess like the expectation, but also like yeah, I don't know. I guess that's like the extent of my knowledge. Just like it creates these three terms and like it can be derived out of EM, and it just basically like creates a lot of nice things like Elbow.
I mean, I would need to like actually see that in writing. I can't. I don't know what you're referring to at the moment. Yeah, but I don't think. I mean, the reason like looking at EM is interesting. It like knowing how EM works is not really like a prerequisite for understanding VAs or anything. It's just an alternative approach to solving like latent variable models. So if like this is accessible to you, like solving it this way, yeah, this is one way to do it. And the reason like this is like possible is because the denominator you can see is tractable. Like it's just a sum. So assuming K is like a reasonable thing, we can just like do K terms, sum K terms, and we're happy. As opposed to integrals, which might not have a, well, yeah, you're generally not going to find like those forms unless like your things are like conjugate or something.
So does the, you say here try an iterative solution only works because denominator is low-dimensional discrete. So if you increase the number of categories, I guess, or like discrete, I don't know what they're called, like bins in your categorical random variable, does that make, what effect does that have? Like, what's the negative effect? Is it just?
I mean, tractability is like, I guess, like relative.
Okay.
So you can imagine if I increase K to like 100,000, that seems a lot. That seems becomes more and more unreasonable because then every iteration I need to do 100,000.
Okay.
Some 100,000 terms.
Sure.
Like similar to how like you can like you can do like GPU regression is like n cubed, where n is like number of data points, right? And like, oh yeah, like why don't we just do n cubed? Like is that kind of question. Like obviously n cubed just gets too big to be reasonable. So tractability is like a relative concept.
Although I do think this is a good maybe segue to think about like, if K was really big, how would you approximate that?
So
Do use some sort of like sampling procedure? I don't know.
Yeah, so I think that's a pretty good step, right? So you can really choose what would be good, what are good Z's. Somehow control most of the mass, and that would be pretty great, right? So, for example, imagine that you're going to model images of numbers, right? Of like digits, 0 to 9, and then maybe the latent was just the actual value of the digit, right? Like the input number, right? If I give you like a picture of a 7, then for most values of these, that's gonna be very low probability. So it doesn't really make sense to like these sums are only like there's only a few leading terms that are really valuable. And in fact, you should really pick the z that corresponds to x, right? Like if you could know that, then that would be fantastic, right?
Yeah. So if you had Oracle,
yeah,
that could
right.
tell you what P of Z was.
Oh no, well, P of z given x.
Z given x. Yeah, that's right.
Yeah, exactly, right? And so this is how you end up. Well, this is the kind of thought process that leads you to doing something like the elbow. When you replace the expectation over all z with the expectation over z given x.
Yeah. Sort of like an important something type.
Yeah, exactly. Yeah, exactly. Like, these are all like somehow like all manifestations of this idea of like somehow this naive sampling style works. Maybe there's better ways, or better sampling schemes.
Mm-hmm. BS. Again, I'm not gonna watch this video, but I'm assuming it's right. But yeah, I don't think it's important to the presentation. But all I wanted to tell you, the reason I'm showing this slide is like bottom tractable. We can do this EM. Tractable because discrete and low dimensional. So now let's actually like solve this for like the more general case. Well, not solve, but approximate it. So we know the denominator is intractable. Let's approximate P of x given z with Q of x given z. So, wow, this is the exact same thing I showed you earlier. Lol. So, okay, this is, I'm not sure this is the right derivation to use given this presentation, actually, given that I've been like talking about inference and not about P of x.
Do you mean P of Z?
No, I've been talking about like this objective. We're interested in inference. But now this derivation starts from P of x rather than.
I mean, isn't that fine because we're approximating Z given X?
Oh wait, yeah, I remember. Sorry, I was. It's been a while since I read this slide. Okay, so the bottom term is P of x, right? So if we could find out what P of x was, or approximate it, then we could solve this. So to start off, let's I'm gonna just model log P of x, but same thing. So I can take imagine I'm taking like a this is similar to what like Sphinx was saying earlier, where I assume there exists some oracle, or in this case not and this is I can say these two things are equal, obviously, because p of x is not a function of z. So these two things are equivalent. And then I can just expand p of x to be equal to the joint distribution of p of x given z. That makes sense, because that's just, well, Bayes' rule, just flipped around a little. And yeah, the q's, obviously I'm introducing the q's, and this is the same thing, so they cancel out. But so I can introduce them on the numerator and the denominator, and that's fine. So given this, I can now, and given that this is a log, I can now separate this into two terms. And p of x, the joint over q of z given x, and then this other objective, which is trying to map q of z given x to the true p of z given x. Make sense?
I don't really follow like the q of z given x portion.
So q of z given x is just like an arbitrary like distribution. Like you could think of it as a distribution that is trying to approximate. Well, you could think of it as anything really. Like, but at the you could imagine at the second step, like it really means like anything. Like it doesn't matter what it is really. It's just a distribution. And then once we define the whole objective, it is maximized when maximized. Yeah, maximized. Not maximized.
So okay, so I guess by being it's like, I know what q of x is in the context of VAE, but like I don't know what it is in this context, specifically the q of x. Q of z given x over, like when you're essentially multiplying by 1, but in the form of q of z given x. Why are we doing that? Like what is it? And then yeah, just that for now.
Right. Yeah, I don't think this is like the best definition to use in the context of this presentation. I can't remember how I like presented this last when I read this.
Well,
but you can see you can see like there are a couple of I'm gonna go like revise what I said earlier. There are like objectives like we care about. One is inference, which is learning a good model of p of z given x. What is that's the very last the right hand side of the KL, the very last term, p of z given x, because that will tell us, given our data, what is the latent variable. We care about that. But we also care about generation. So besides inference, we also care about generation, which is p of x. If we have a good model of p of x, we can generate, because that just involves something from p of x. Or rather, like So actually, no. That is essentially what we want to learn, right?
So you should be a little careful, right? Because you can definitely learn PFX and not learn a useful PFX in Z, right?
Yeah. So that's why I'm defining two objectives.
Okay.
So I remember writing down something, which says, if you assume like latent variable, like if you're doing a latent variable model, so there is a Z that really exists, or it is part of your modeling decision to include a Z. I think you still end up with the elbow, even if you only care about P of X.
Yeah, but the elbow doesn't guarantee that you'll get anything useful if you're
For inference.
sure. Yeah.
For inference.
Yeah, correct. Like you can model PLX perfectly fine, but your latent variable can be useless. Just like the whole auto encoding single bit.
Yeah. But yeah, I'm also talking about the objective, like, will end up being the elbow. With those assumptions. But yeah, just taking a step back, we care about generation, P of X, and inference, learning P of Z given X. So we want to maximize P of X and or log P of X, and minimize. If you take Q as a surrogate distribution that is going to approximate P of Z given X, then we want to minimize that, minimize the KL here, because KL is always positive.
I have a question. I don't know if you're going to come to it eventually. Why is it called the evidence lower bound? What is the evidence and why is this a lower bound on that?
I'm not sure if it's apparent from this derivation. So the evidence generally refers to P of X
Yeah, true.
and Z.
Not in visual.
Yeah, so why is it the evidence lower bound?
I think you're missing like one line of like commutation. So like the term on the right is currently intractable. So
Yeah,
if you do a little more
I need to
algebra,
move it.
then then this will
Yeah.
give you the evidence there.
Yeah. So yeah, that's what I was getting to with maximize this, minimize this. Let's put like what's the most obvious way to do that is just obviously log P of X minus the KL. Then if that is like the objective we care about, that's obviously giving us the elbow, which is what I've underlined here.
Why is the probability of Z given X like Z given X? Why is that intractable?
P of Z given X, why is that intractable?
Yeah.
Because to do the elbow, you need to know. I mean, we don't know what P of Z given X is, right?
Yeah. Right. Okay.
Yeah. So, in fact, we can't even sample from it. Like, we don't even know what to. So, yeah, completely intractable, right? I'll find a better derivation, and that is like more closely fits the narrative I've been doing. But that looks like a hacky fix there. Oh yeah, and then expanding this, you get this, which is the elbow you're familiar with because the final form.
expand meaning what changed, what's different from this last equation?
I mean, I think all that changed was like the addition of like these parameters.
No. See, no, you're not paying attention, right? So for example, notice in the KL term on the second thing on the right after the two bars, it's only P of Z.
No, I'm thinking about expanding this elbow.
Oh, just well, you mean just this first term, I see.
Yeah.
Right, but
The first term is what's like the first term. It's where I start off the derivation, the expansion.
Oh, I
So,
see.
joint
Yeah,
over
I see. Yeah, I think I misread. Might be. Yes.
I felt the same way. I clarified this.
Yeah. Yeah, I think the key thing to realize is like, so this is what I was trying to say earlier when you're saying like, oh yeah, like, the plot we're trying to approximate is like prior. Oh, we have the prior, like, don't need to approximate it. It's just like a objective. This is the true posterior, the P of Z given X. And that is what we want to minimize. So that's why we're doing log P of X minus this K equals the elbow.
We don't actually have prior, we just have the idea of prior.
I mean, the prior is up to us, by definition.
Yeah.
It's like what we choose it to be.
Maybe it's also worth noting that we can actually discard the other KL term, but we cannot discard this one. So it might be good to think why that is.
Sorry,
So why does this suffice to optimize the elbow? And not elbow plus that thing.
Yeah, this was something I never understood when I was trying to follow the derivation from expectation maximization to elbow, is that there's this like third term. This person that I learned it from calls it like the index code mutual info or something like that.
Yeah, it's like in general, you should always avoid using things that sound like prose. It's like it sounds good, but it means nothing. So.
Yeah, I have no idea what it means. Like it.
Yeah. No, but I'm saying, why do you think we can get rid of that KL term, but not this one here?
Wait, you think get rid of this KL term?
Yeah, I mean, think about it. We optimize elbow. We don't optimize elbow plus that thing. Right?
I mean,
it's good because we can't actually touch that at all. But I'm saying, why are we allowed to ignore it? This is more of a you paying attention, I think. Well, no. It's just like give me your thought process. Like, why is it that optimizing elbow is no? Or even good, right? Like what we can ignore the KL term there.
I don't think we can. I thought the KL was like the regularization term that like we
Mm-hmm.
had.
I'm using your KLs.
Yeah. There's two KLs, right?
Who's like is that? Assuming is helpful.
I got it.
Yeah, so I guess yeah. So my understanding as well is that there's like a positive KL and a negative KL.
Expand.
That's all I know. I can't expand.
No, but try to reason out from what I want to show you here. So here we have like this first term, which is the elbow, as we showed in the next slide, and then we have this other term, which is KL, right? So you have, so like I said, there's two KLs, right? You have one with minus sign, one with positive sign. That's what I imagine you meant by negative positive. So why so that we can get rid of one and not the other?
Without having it right in front of me, I don't fully know, but I would imagine it's like the other term is the KL in respect, like it's the KL in respect to the, like if you were to flip it, like it's P of Z given X, whatever the double part symbol means, QZ of X. It's like if you were to like take the KL in respect to the opposite way it's taken here.
So we know what the KL term, right? It's like what comes up in the elbow. Okay, so you agree that this KL term on this slide is not the KL term from the elbow, right?
I honestly thought it was.
Okay, so now that you're looking at it, why do you think it's not? Like, what's
Sorry,
the
just tell me to switch slides if you want me to. Hold on.
Yeah, yeah. So, so what's the difference between this KL and the other one in the next slide?
For approximating x given some weights.
Okay. So ignore the capital lambda and the data, I guess.
I don't know that.
No, but
I mean, other
there.
than
This is like just image recognition, right? What's the difference? Like, if you go back and forth between the slides.
is there a negative term?
No,
One's
but
plus,
the actual
one's
tail
minus.
term, right? Like, look at the distributions. They're different.
Okay, can you go back?
Oh wait, no, this is a read-only PDF. Sorry. kind of.
What is different here? In just the KL term, I don't see the difference. Like
Yeah,
other
look
than
at-
like if I were to ignore. I'm sorry.
Look at the thing after the two bars. So that's when the one has highlighted, or not highlighted, but under. Okay, so that's so what is that? Say it. The term is a PFZ given x, right?
Yeah. So the other one approximates it with weights.
No. Don't say words. Just identify it first, and then think of what you're gonna say. Right? Go to the next slide. Okay. Now what is that term?
Beta.
Okay, but you use no x, right?
Yeah.
Yeah, that's so it's very, very different. Right? So we know PFZ, but we don't know PFZ given x. So one is tractable, the other one is not. One it corresponds to elbow, the other one corresponds to some shit that we just cannot do anything with. But we can get rid of it. Like, that's why it suffices to only do elbow. But the question is why so that we can get rid of this one and not also get rid of the other shit.
I don't know what the other KL really means. What does it mean to say PFC given weights?
But don't worry about the weights. The weights are just
Yeah.
distract.
Imagine the thetas and the lambdas didn't exist.
Yeah.
Okay, that makes it even more good. So like PFC given nothing.
Yeah, sure.
Yeah, TFZ.
Just PFZ.
Yeah.
There's no bar.
Yeah.
Oh, okay. Yeah, sure. I mean, that's just as arbitrary as like.
No, that has a meaning. Like Bun has been talking about this for like, wow, what is the meaning of PhD in terms of words?
In terms of what?
Like, so I think Bun has used a few terms. So like he used like evidence, he used prior, posterior. Which of those words corresponds to PhD?
It is ultimately related.
Okay, but so I gave you three options, right? Prior, posterior, and evidence. Which one would you use to describe PhD?
Prior.
Yeah, exactly, right? So like that has a meaning, and we know what the prior is, right? Because we can choose it. But PhD next, right? We have no control. So that's just like it's just something that it is where it is, right? We don't necessarily we may not be able to actually capture it without some additional or something else.
I see. Yeah, that makes sense.
So this KL is good, or like I don't know if good, but at least we can work with it. But the other one is like not good.
Okay, yeah, I see.
So now, why do you think we can get rid of the not good one?
I mean, we're not really getting rid of it. We're just like simplifying it. Just like
No, right? Like, we are definitely getting rid of it. Like we don't optimize it. Right? We only optimize the things that we undermine.
I mean, like, I don't know. It seems like like sure we're getting rid of it and substituting it with something else in the same way that like we don't use like infinity in the denominator. We use like some arbitrarily large number, right? It's just like
No. But we're not substituting anything, right? Like we substituted the first term for two terms, but that thing's still there, right? Like, and then we're just ignoring it for some reason. Like, do you agree that like if you in the next slide, right, he writes the equation for the underlying term, right? So if you put those, so if you add the other KL term, right, now you have the log term, like the first term, the minus KL term, and the other KL term, right? But you only optimize it. What?
why would you do that?
What do you mean? Well, I mean that's part of the equation. What do you mean? Like, it's there. Like, there's two terms here, right? And then in the next equation, he writes the first term as two more terms. So you should have two terms. Right? Those two terms plus the other term.
Sorry, can you go back one minute? Okay, and then can you go like?
So you can see how like this thing I underlined here.
Yep.
That's where I start off here, right? That's like the first thing. Like L equals that.
Yeah.
You can see like joint over Q z given x. This is joint over Q z given x. Yeah. And all the rest of this is just expanding this into the elbow. This is just like a very concise way to write the elbow. But you can see I've expanded it to what is on the bottom. It should be familiar to you. Yeah.
Yep.
So this is two terms. Now, going back to this equation, I replaced this with the two terms I just expanded it into. Right?
Yep.
So now I have three terms. Those two terms plus this additional KL term here.
Oh, okay, sure. I see.
So Sphinx's question is, why is it okay to just optimize the elbow and ignore this?
Because in theory this should equal the, or I should say the elbow term should equal this term.
No.
What? How? How's that not true?
Yeah, but why would it? You couldn't give like what the
Well, in theory that our, like, whatever way we're modeling this unknown, PZ given X, well, I guess taking from a different way, like, if you were to just, like, expand this to have all their terms, such that, like, the negative KL term is PZ given, theta. Theta should thus approximate, like, theta should ideally be equal to x. Like, I get its approximation, but, like, ideally it should equal x. So, negative KL plus KL should equal 0 regardless.
But then, by that logic, why do we have the KL term in the elbow? Right? Why not just optimize the first term like the construction? And besides, so even ignoring that, right, you will still have to optimize that third term, right? Like what you're saying would only be true at the optima somehow, but you wouldn't have no way of controlling that directly.
Right, but like we have no way of ever measuring it, so like that's why we drop it. Like,
No. I mean that's why we need to drop it, but we have to justify dropping it. Right? Like if we couldn't justify dropping it, like this wouldn't be published because it would be like 100 years and not really good. Like there must be some reason why it works to drop it. Like it's not like Kingma was just like, oh yeah, let me just try dropping it for fun and see if it works. And like he had some justifications of why this was like fair, and the fact that it works says that yeah, that's a fair justification.
I'm thinking. Let's see.
Yeah, I guess that's a hint. Like the answer's in the name of the method, or the objective. I guess it's.
Yeah, I don't know. I mean, the only thing that I can think of is that by estimating the priors, given some posterior that we use to estimate the prior, that we will be like it will create a value that is equal to that of if we were to have had the extra term. Like the error associated with like guessing the priors will inherently have this added term.
I mean, guessing the priors.
Well, the prior is completely unknown to us, right? And
No.
No. We know the prior. We chose the prior.
well, we assumed that it was some value, but like the true prior, we have no idea.
There's no concept of true prior.
Yeah, this is what we assume.
Okay, still, like, even like, actually, I don't know if this is completely true, but like, even if we use a really nice model that estimates like the that best estimates the prior, there will be error
Once again,
associated with.
there is no estimating the prior. The prior, we choose the prior, so we have 100% accuracy on that. If we choose
Right.
what it is.
But like, we're not God. Like, we don't know the prior.
We do know the prior. We choose the prior. That's the one thing we do know. Like the prior is whatever we want it to be, right? Whether it works out and gives us a good model, who knows, right? But we can choose the prior. It could, yeah.
Okay, sure. We choose the prior, but estimating the prior.
Graph.
That makes no sense. Don't say
So-
estimate the prior.
I think you like is the issue like okay instead of saying like prior, tell me the form which distribution, like p of what.
P of X. Sorry, P of Z.
Okay. Yeah, I thought it was like terminology problem.
Yeah, I mean that's the one thing we do know for sure without any estimate or modeling prior.
Right, but the prior is a mixture of Gaussian, right?
No. Like I think for the purpose of this math, the prior it doesn't matter what it is. Yeah.
That's what I have here. this is our prior, right? We have like this. I don't know the term for it.
No. Okay. Stop. Like, the objective is to learn the posterior. I mean, to learn P of C given X, right? Or at least that's one of the objectives. Or even if you just wanted to learn P of X. But in like nowhere is our objective to learn P of Z. Because like we define it. So even though there exists, like, just because a KL term exists for it, doesn't mean like we want to learn it, right? Like doesn't mean like we can't approximate it. It's like just an approximation or anything. Like if two distributions are defined, like then I can just calculate the KL. It doesn't mean I'm trying to learn P of Z.
Okay.
I don't know, like maybe this derivation, like the way we're doing this derivation isn't for you. Like maybe you should look at a different way. There are like a million ways to derive the elbow. It's just
No,
one way.
I mean that makes sense. It just, yeah, I used it. It makes, yeah, I guess that makes sense. Like we don't care about it.
No, but you can't just say we don't care about it. Therefore, it's okay to ignore it. That is like not a balanced strategy.
Well, the function is with respect to x, not z, right? We're just using z as a way to best approximate x. If we're just solving for p of z, why do we care about that? Isn't that what you're saying?
No.
We're not solving for P of Z. Well, once again, we know P of Z. It's the one thing we do know.
Right, but the function isn't with respect to it, right? So we can drop it because it has no bearing on like what we're trying to solve.
But it does have bearing. Like there's like it's
Just
just like
this term like on the right has a dependence on Z.
yeah.
This intractable term that you want to ignore, but you need to justify, adds a dependence on Z.
Yeah, I don't.
I can't optimize P of X directly because there's this intractable bit, right? And the intractable bit is a function of Z.
Yes, then I don't know why we can just get rid of it.
Sorry, could you say the question again? Like, what are we trying to answer here?
Right. So, do you follow this derivation like on this page?
Oh, definitely not.
What parts are challenging?
So you're taking the log of a probability function, of a probability of some x, right?
Yeah, a log of density.
And then, let's see, and then you mysteriously get some special e that's the part that's most
E
confusing.
is an expectation.
Okay, so it's the expectation of, what does the q function mean?
So the Q is like some arbitrary distribution I define.
Of z in terms, z given x.
Yeah. It's supposed to approximate like the true posterior, but we only see that later. Like this is just like a quick like way to derive it. But you could imagine it as like an arbitrary distribution.
And then how does p of x jump into that massive what is the numerator and denominator? Is that the question here?
No. So the way it goes from P of X to this is P of X can be written as like this joint distribution
P and Z and
divided by this
is
condition.
B.
So P of X equals joint over conditional just by base rule or something. Not even base rule, by product rule. And then the Q's appear, because they're the same, I can just add them to the numerator and denominator, they would cancel out. So it's just me doing that.
Right.
Yeah. I don't know. Maybe next time, like, I'm not gonna continue this presentation just because it's kind of late for me. But I think it might be helpful to like see different elbow derivations. Really, like, because there are a lot of different ways. This is just a very concise way of driving it. But there are other ways. I think I used this derivation because of its connections to EM. But yeah, so just to end it, the question was, after you get to this final line here, and what is underlined is expanded upon in the next slide into these two terms. So I can take those two terms and just sum them in here, and now I have three terms. Now the last term, L Q Z given X, P Z given X, is intractable. And when we do variational inference, we only optimize like the first two terms, so the elbow, what's underlined. So we're ignoring the last term.
So
The question is like, why is it okay?
I put in the whiteboard chat, like explicitly kind of what you in later. So you have equation 1, you just got like it's the third from the bottom. You have the first equation, equation 1, and then somehow, okay, this is the question, why is it possible that we can just like go see ya to the KL divergence and equivalently maximize the second term? Equation 2. That's the question. Why is that the same? Why is that okay?
Yeah, I mean, the objective is obviously changing.
Yeah.
So when we optimize the bottom equation 2, we're no longer optimizing log P of X.
I think maybe people's understanding of Kerr divergence is the reason why this question is so challenging. In my opinion, this could be why. Because probably the thing you need to see relies on a fact about the Kerr divergence.
Yeah, you got it.
Can you explain?
Sure. So the Kerr divergence. Okay, this is not technically a correct intuition of the Kerr divergence, but if you think of it as a distance measure between two like probability distributions, wrong intuition, but it'll do for now.
Oh, I think I see. Like, because we don't have access to X, we can't actually determine like the Z onto X, like the similarity of Z onto X.
Not quite. So no. So okay. So if you think so our goal, right, is to maximize equation